Welcome. In this video, I want to go over the solutions to the Paper 2 questions on Topic 1. Topic 1 is undoubtedly the most difficult topic because it really incorporates all the chemistry you've learned in 2 years. So I'm going to try and give you some strategies to not get overwhelmed when you see Topic 1 questions, especially in the free response section. So number 11, they give you a bunch of information, percent of nitrogen, carbon, the conditions, and then you notice that's worth 3 marks, and they're asking you for 3 distinct things: empirical formula, molar mass, and molecular structure, which is a lot for 3 marks. So there must be fairly direct solutions to each of these. So as far as empirical formula, you need to take the 53.8 grams of nitrogen, divide by the molar mass of 14.01 grams per mole. Remember, the 53.8% is mass, so that's, you could just think of it out of a 100-gram sample. And when I do that, I get 3.84 moles of N, or nitrogen. I do the same thing with the 46.2% of carbon. I think of that as grams of carbon, and divide by 12.01 grams per mole, which gives me 3.85 moles. And I see I have the same molar amounts of nitrogen and carbon. So this is going to have an empirical formula of CN. Now, if you wrote it NC, that's fine. Technically, it'd be CN. Remember, we kind of write left to right on the periodic table. You might recognize that as cyanide. So that was the first mark. Then they want to know the molar mass of the compound and determine its molecular structure. Well, the molar mass is a little messier because they give you the conditions to use PV equals nRT, but they're not very nice about it because V is in centimeters cubed, so I need to change that to 0.462, and P is in pascals, not kilopascals. So to use PV equals nRT, you have to convert P to 1.01 times 10 to the second, or 101 kilopascals, and you're just going to have to get used to 1 atmosphere to the rest of the world is 101 kilopascals. And then my V is 0.462 liters. And now that I have them converted, I can calculate N. The only R value they give you is 8.31, and again, that's for kilopascals and liters. And then T, they did give it to me in Kelvin at 273. So when I solve for N, I'm coming up with N equals to 0.0205 or 0.0206 moles. But I'm not done there. That's not my molar mass. My molar mass is my grams per mole, and they told me my sample was 1.048 grams, and I got 0.0206 moles. I apologize. They don't give you much room on some of these questions, and my software doesn't let me edit that at all. So when I take 1.048 and divide by the 0.0206, I come up with the molar mass of 50.87 or 50.9 grams per mole. So that was my second mark. So again, a lot of work for 2 marks. So you have to prioritize. Go with what you know. That on number 12, there were much easier questions for a mark each. So then the last one wants to know its molecular structure. Well, I need to know its molecular formula before I can determine structure. So up here I see that 1 carbon and 1 nitrogen would be a mass of about 26, but this is closer to 52. So apparently my molecular formula is actually C2N2, or CN2. And so what that means, if I think about CN2, my 2 C's should be in the middle. So I single bond them, and my ends then are going to triple bond to it. And that would be my molecular structure for the final mark. Number 12, this was far easier than what a lot of you made it. So let's walk through it a step at a time. What made number 12 nice is they spread it all out for you. They led you 1 step at a time as to what you were supposed to do. The percentage by mass of calcium carbonate in an eggshell. So calcium carbonate is 1 part of an eggshell, not all of it. It was determined by adding excess hydrochloric acid to ensure that all the calcium carbonate had reacted. So you know calcium carbonate's your limiting reactant. You know all of it has to have reacted with HCl. So then you have extra acid left, and you titrate it with sodium hydroxide to find out how much HCl was left over. So A, a student added 27.2 centimeters cubed of 0.2 molar HCl to 0.188 grams of eggshell, calculate the amount in moles of HCl added. Well, here's my HCl information. The 1.88, that's the whole eggshell. Some of that's calcium carbonate. They're asking me about HCl right now. I added 0.02720 liters, and it's got a strength of 0.200 moles per liter. So I simply multiply those, and I have 0.00544 moles of HCl that was added. That's not how much was used. I know I added extra. The excess acid requires 23.80 centimeters cubed of 0.1 molar NaOH for neutralization. Calculate the amount in moles of acid that is in excess. Well, HCl plus NaOH is just going to be 1 to 1. It's going to give you NaCl and H2O. So if I go ahead and take my 0.02380 liters of NaOH times the 0.100 moles per liter, I see that I have 0.00238 moles of HCl, and I know that 0.00238 moles of NaOH, I know it reacts 1 to 1 with the H and HCl, so I can also conclude I have 0.00238 moles of HCl. Now again, up here, 0.00544 is what I added. This is what I had left over. So determine the amount in moles of HCl that reacted with the calcium carbonate. Well, I added 0.00544. I had 0.00238 left over. If I subtract those, then I know I used 0.00306 moles. That's how much reacted with the calcium carbonate. They're walking you right through the process. State the equation for the reaction of HCl with calcium carbonate. You should have been able to get the reactants. HCl, CaCO3. Carbonate needs 2, calcium gives 2 electrons. Now, as far as your reaction, it's going to be a double replacement, so you should have come up with the CaCl2. Now, if you left the H2CO3 together, not the end of the world, because it's not going to affect any of your calculations. But remember, with carbonates, it breaks down into CO2 and H2O. But again, it's not going to affect the balancing. What you have to notice is that the CaCl2, I need 2 chlorine there, so I need a 2 here, which balances with my H2O. And that's important because now I've got a 2 to 1 ratio with the calcium carbonate and the eggshell. Now, up on A and B, if you could come up with answers, if you just filled in answers and subtracted them for C, I still would have had to give you a mark there. So be shrewd about this. Take your marks where you can get them. As I go over to the next page and finish this up, determine the amount in moles of calcium carbonate in the sample of the eggshell. Again, if you weren't able to come up with showing calculation for your moles of HCl, make up a molar amount back on the previous page for your moles of HCl used, because then you can take that molar amount of 0.00306 moles of HCl used, or whatever amount you make up so you have a number to use, and you can show that you would take it times the 2 to 1 ratio of calcium carbonate to HCl, and you would know that you have 0.00153 or half as much calcium carbonate. That's what you're getting your 2 marks for, is knowing that, and I don't know why they gave you 2 here, because all you're doing is a molar ratio. Then finally, calculate the mass and the percentage by mass of calcium carbonate in the eggshell. Again, take whatever number you made up in E, because they do not penalize you for carrying a wrong answer forward. I simply grade you for if you're doing the next step correctly. So this is my calcium carbonate times the 100.09 grams per mole that calcium carbonate weighs. And I come up with a mass of 0.153 grams. Now finally, to get my percent by mass, 0.153 grams. And if I go back to the previous page, remember it was 0.188 grams of eggshell times 100% is 81.4% calcium carbonate in the eggshell. Letter G, deduce one assumption made in arriving at the percentage of calcium carbonate. Common assumption people made was that calcium carbonate all reacted. They told you that. They told you they deliberately made HCl in excess so all the calcium carbonate would react. So that's not an assumption. That was a given because you put in excess HCl. There can't be any calcium carbonate left. That's how excess and limiting reactants work. So the assumption you can make is that only calcium carbonate reacts with HCl. Nothing else in that eggshell also reacts with HCl because that would throw your numbers off. So that's the assumption they were looking for. Number 13, the picture showed up on this page, but that's okay because you really don't need the pictures because these are organic formulas we haven't looked at yet. What you would need these pictures for was for question A, the 3 organic functional groups, which we'll be getting into. OH is a functional group, COOH is a functional group, this benzene is a functional group. This is also considered a functional group here. That's considered a function. So there's functional groups all over. I didn't care about part A. I meant to let you know that that wasn't going to be counted against you. But so if we go to the actual question part of this, if we omit A and not worry about functional groups for right now. Again, part B walks you through the steps you need for this if you just don't let IB intimidate you. A student reacted some salicylic acid with excess ethanoic anhydride. So those are the 2 reactants they showed on the previous page. Complex looking structures, but look, right here, they give you the formulas for them. You don't have to know what that structure means. Impure solid aspirin was obtained by filtering the reaction mixture. Okay, so they're attempting to get the aspirin separated from any leftover reactant and any of the other product. Pure aspirin was obtained by recrystallization. Okay, so they filter it out as a liquid, they recrystallize it as a solid, and separate it. So here's your reactant used, 3.15, and there's the pure aspirin you obtained. This is your experimental value. So this mass of salicylic acid up here, this lets you calculate your theoretical value. You always have to calculate the theoretical based on what you started with. What you recovered, that's your experimental value. So determine the amount in moles of salicylic acid used. Well, I used 3.15. They're not asking me to do anything with the uncertainties, so I just leave it. I have 3.15 grams. And when I look at salicylic acid, I see 7 carbon, I see 6 hydrogen, and I see 3 oxygen. So I can figure out that 1 mole of that weighs 138.13 grams. And this is 0.0228 moles. That's how much of my reactant I use. So calculate the theoretical yield in grams of aspirin. Well, when I look at my pictures on the previous page, it shows me that my 2 reactants react 1-to-1 to produce 1 mole each of my 2 products. So I can assume I also have 0.0228 moles of my aspirin. And now when I look at my aspirin, I see that I have 9 carbon, 8 hydrogen, and 4 oxygen. So I could come up with a molar mass of 180.17 grams per mole of aspirin. So here's my theoretical yield is 4.11 grams. Now again, if you were stuck on these, come up with an answer and circle it so you can use them in later questions, like determine the percentage yield. You should know you need to take 1/2 to get the percentage yield. So plug some kind of number into 1 and 2 and then set it up here. Actually, I guess I just need 2 because here's my experimental yield, 2.5. So you should have known that goes on top. And now plug in some value from part 2, 4.11. Take it times 100% and get a mark here. The correct answer would be 60.9%. The last two questions actually were not bad at all. But again, I get that this is overwhelming, and by now your confidence is shattered. That's what we need to practice. Do not let them get into your head. State the number of significant figures associated with the mass of pure aspirin obtained. What says 2.50? That's 3 sig figs. Nothing tricky about that. 3 digits. That's it. Calculate the percentage uncertainty associated with this mass. Well, the uncertainty is 0.02 out of a total of 2.5. Let me just clean that up for you. Out of 2.5 times 100%. That's a percent uncertainty of, let me just see my number here, of 0.8. 0.80 to be exact. That was 2 easy marks for doing a percentage. Another student reported the experiment and repeated the experiment and obtained an experimental yield of 150%. The teacher checked the calculations and found no errors, so comment on the result. What they're getting at here is that the error is in technique. IB is assuming the teacher doesn't make mistakes, which I think is a fair assumption. So calculations aren't the problem. So calculations aren't the error. But technique has to be. Because 150% yield isn't possible. We know that. So what could be the possibility there? It could be that the sample isn't pure. Why not? The aspirin is still wet. Remember, they filtered it and then recrystallized it. That means they turned it back to solid. So if the aspirin is still wet, the water is going to make it heavier than it should be, make your yield higher. Or maybe it's not pure. Maybe it didn't get all separated from the other reactants, whatever your excess reactant, or from your other product. But something's wrong with your technique. That's what they're looking for you to realize.